Okay, our next speaker is Rebecca Tenney from City University as well. And she will talk about exactly solvable time-dependent non-Hermitian quantum systems, and from a particular point of view, which is point transformations. So when you're ready, Becky, go ahead.
Thank you. I'd first like to start by thanking the organisers for giving me the opportunity to discuss this work here today. It's been done with my supervisor, Andreas Ring. Recently, we've been looking a lot at new methods for determining Dyson maps for time-dependent non-Hermitian systems. So we've looked at some approximate methods and exact methods, and this is one of the exact methods which utilizes point transformations. It is based on this paper here. So the outline of my talk, I'll start with a very brief introduction. I only want to say what PT symmetry is really, because something very interesting happens with the model that we're considering later on. I'll then move on to time dependence in non-Hermitian systems, cover the key equations, which I'm sure many people know. So the time-dependent Dyson equation, the time-dependent quasi-Hermeticity relation. These involve two important quantities, being the Dyson map and the metric. I'll talk about why they're important to calculate first when studying time-dependent quantum systems, and then I will go over the different solution procedures. This will allow me to motivate why we want to use point transformations with time-dependent non-Hermitian quantum systems. I will then give a brief introduction to what point transformations before and cover how they've been used for Hermitian systems and how we wish to extend their use to non-Hermitian systems. I will then apply this all to the time-dependent Swanson model to determine the Dyson map, and then present any conclusions. Okay, so to start with, it's something we all know now. Hamiltonians do not have to be Hermitian to have real eigenvalues. They can be PT symmetric. So standardly, we know that for a one-dimensional Hamiltonian under PT, P goes to P, X goes to minus X, and I goes to minus I. And the same picture that Taka had before that we're all familiar with, showing that the eigenvalues are real for this Hamiltonian if epsilon is greater than 0. I'll just move on now to time dependence. So when dealing with a time-dependent non-Hermitian quantum systems, the starting point really is two separate Schrodinger equations. So one for a Hermitian Hamiltonian, which I've written as little h of t, and one for a non-Hermitian Hamiltonian, which I've given as capital H of t. You can relate the solutions to these two Schrodinger equations through this relation here, where eta of t is referred to as the time-dependent Dyson map. This Dyson map is not unitary, it's not unique, and it doesn't have to be Hermitian. If you plug this relation here into the equations, you can pull out what is known as the time-dependent Dyson equation, which relates the Hermitian Hamiltonian and the non-Hermitian Hamiltonian via the Dyson map. Another important equation that you can pull out is found from conjugating this equation, which is the time-dependent quasi-Hermeticity relation, which involves the metric rho of t, which can be constructed from the Dyson map. Now, the Dyson map and the metric are obviously very important in terms of these equations here, but also in terms of observables for these systems. So we know that in the Hermitian system, observables, so little o of t, are self-adjoint. In the non-Hermitian system, they are quasi-Hermitian, are in fact related to those in the Hermitian system through this similarity transformation here. And we can actually standardly calculate observables through this equation here. But what is important about this observable equation here, if we look back at the time-dependent Dyson equation, is that the non-Hermitian Hamiltonian h of t isn't actually observable due to the presence of the time derivative term. So when studying these time-dependent non-Hermitian systems, you have to define a new energy operator using the metric or the Dyson map. Therefore, when you're studying these systems, you really must start by calculating the metric and the Dyson map. It's very important. And there are many ways that you can go about calculating them. Firstly, you could solve the time-dependent Dyson equation directly for the Dyson map. And then from here, it's straightforward to construct the metric. You could instead solve the time-dependent quasi-Hermeticity relation directly for the metric. However, here it can be a bit more harder to determine the Dyson map. Even if the Dyson map is real, when you take the square root of the metric, you don't know if you're taking the positive or the negative. But what both of these solution procedures have in common is that there is a time derivative term in the Dyson equation and the quasi-Hermeticity equation. So when you do actually go about solving it for a system, you end up solving sets of coupled differential equations, which can get quite involved. So luckily, there is a third method, which uses Lewis-Riesenfeld invariance. In this case, you find an invariant for the Hermitian system and the non-Hermitian system, which satisfies this equation here. And then from here, you see that they're actually related via a similarity transformation. So it's much simpler to solve for the Dyson map and then construct the metric. And also, once you have the invariance, you can then find the full solution to the time-dependent Schrodinger equation. So you have that the invariants satisfy this eigenvalue equation here, where the eigenvalues are importantly time-independent. And then you'll only have to find this phase here from this equation, and you have the full solution to the time-dependent Schrodinger equation. But one drawback, I would say, of this approach using the Lewis-Riesenfeld invariance is that you're usually relying on making an ansatz for the invariant. And finding this invariant can get incredibly difficult with more complicated systems. So we wanted to find a way to bypass that need for the ansatz for the invariant. And to do that, we wanted to use point transformations. Point transformations are usually used to find solutions to partial differential equations in terms of the solution of another partial differential equation. And recently in this paper here, they've been used to look at Hermitian time-dependent Schrodinger equations. So in this paper, they found the solution to the time-dependent parametric oscillator by constructing a point transformation between that system and the time-independent stationary harmonic oscillator. And they got all the solutions from it. And most importantly, what we're really interested in is that these point transformations preserve conserved quantities. So when you take this point transformation and act directly on the time-independent Hamiltonian, so in their case, the stationary harmonic oscillator, it produced an invariant for the time-dependent parametric oscillator. So we wanted to take that and extend it to the non-Hermitian regime to produce non-Hermitian invariants for us. So to do this and then eventually end up determining Dyson maps, we consider like a four-step approach to doing it. So to start with, we have two time-dependent Schrodinger equations, one involving what we call the reference Hamiltonian, H0 of chi, which is time-independent, and its space and time coordinates are chi and tau. We then also have another time-dependent Schrodinger equation here for an explicitly time-dependent Hamiltonian, which we will take to be non-Hermitian, and we will refer to as our target Hamiltonian. In the second step, we now need to construct a point transformation between these two time-dependent Schrodinger equations. So essentially what we're looking for is chi, tau, and psi in terms of x, t, and phi. Once we have then constructed that point transformation, we can use it to act directly on the reference Hamiltonian to produce the invariant for the target Hamiltonian. This invariant will satisfy this equation here, and as mentioned previously, will be related to a Hermitian invariant via just a similarity transformation, making it much easier to determine the Dyson map. Once we have that Dyson map, we can then straightforwardly compute the metric through this relation and the corresponding Hermitian Hamiltonian using the time-dependent Dyson equation.
Philip has a question.
It seems that this might not be a covariant approach, because what you're basically doing in going from chi to x is a general coordinate transformation. And the Hamiltonian is not a general coordinate scalar, it's the fourth component of a 4-vector. So I would have thought you might have mixed, when you made that transformation, you might have mixed in with the momentum operators. But maybe you don't need it, I mean, it's okay.
No, so this is just based on the solutions for the equations and chi and tau, that's all we need for this.
Oh, okay.
Over.
Yeah, there's another question closely related. When I'm looking at your technology and I'm comparing this technology to the well-known papers by Qinghai Wang and by Ali Mustafa Sadeh, they considered actually vibration as similarly as Philip indicated. So you have a vibration and you are looking just for the covariant derivative on this vibration, and this defines you a kind of parallel transport of the energy and so on. Did you somehow relate your calculations to those results just to see the differences and whether they are coinciding or they are different?
Did they construct invariance?
They had covariant invariance, yes.
No, invariance. The Lewis-Riesenfeld invariance.
Okay, okay.
That's the key point here. That's the key point here, to construct invariance. I think it's not related at all.
It's not related. Okay.
No.
Okay, thank you.
Should I continue?
Okay, yes. Uwe has his hand still up, but I think it's answered, no? Yeah.
Yes, it's answered. Thank you very much. Yes, it's answered.
Okay. Now that I've detailed this four-step approach, I will now apply it and show how it works. For starters, we need a choice of reference Hamiltonian. We wish to pick one that's well understood, exactly solvable, and so on. So we chose, as was in the Hermitian paper, the stationary harmonic oscillator. We now actually relax the dependencies of chi, tau, and psi on x, t, and phi. So chi is now just a function of x and t, tau is just a function of time, and psi is now just linear in phi. We do this because it simplifies the calculation, but it also ensures that there are no nonlinearities present, because the Schrödinger equations we're considering don't have any, so we don't want any in these solutions, and this was how we could achieve it. Now that we have this, we can compute some total derivatives, which would have been more involved if we'd have kept all the dependencies we had before. And we can solve these for psi chi, psi tau, and psi chi chi. So what's in the time-dependent Schrödinger equation for the reference Hamiltonian. And once we've solved for these and we substitute it into the time-dependent Schrödinger equation, we pull out this equation here. So it's a point-transformed time-dependent Schrödinger equation, where B0 and B0 are given by these equations here. So it's differential in chi and A and so on. And we would compare this directly with the time-dependent Schrödinger equation for a target Hamiltonian, and then solve for A and chi and tau. There are other choices of the reference Hamiltonian. So we also looked at the free particle Hamiltonian. So here B does not change, but V does. We looked at the harmonic oscillator with the linear term. B again doesn't change, but V does. And then we also looked at the harmonic oscillator with just a linear, with a anti-commutator XP term. Here both B and V change. So we now need to pick our target Hamiltonian, and we picked the time-dependent Swanson model as given here, which is non-Hermitian for alpha tilde being not equal to beta tilde star, and where A and A dagger are defined as here. We obviously need to write it in terms of X and P so that we can compare it with our point-transformed time-dependent Schrödinger equation. So we do that and we make these changes here to the time dependencies. And this is what we end up with, where here we have that M and omega are real, and we're actually taking our alpha here to be complex. This is where it gets a little bit weird with the PT symmetry and why I wanted to mention it earlier. So standardly, as I said, with the one-dimensional Hamiltonians, we have P goes to P, X goes to minus X, I goes to minus I, and we demand here that for this Hamiltonian to be PT symmetric, that M, omega, and alpha go to M, omega, and alpha. But our alpha is complex, so it has a real and imaginary part. So we demand that the real part, alpha R, goes to alpha R, but we require that alpha I goes to minus alpha I. This may not be readily seen here how that happens, but once we construct the point transformation, it does all come out nicely. So now going on to constructing the point transformation properly. So we have from before our point transformed time-dependent Schrödinger equation, and we also have a time-dependent Schrödinger equation for our target Hamiltonian. So we now need to compare these equations. So we have three constraints which come out. One that's in front of the phi x terms, one that's in front of the phi x terms, and one that's in front of the just phi terms. Solving these constraints here can get quite involved and quite technical, so I'll just present the main parts of the solutions that are of interest here. Firstly, we find that we have to parameterize our mass like this, where sigma is some auxiliary function, which I'll talk about later on. Tau becomes this, and our chi here is this function where gamma is just an integration constant, which I'm now going to set to 0 because it makes it much easier to explain and have everything on the slides. A function here is given by this, where delta is again an integration constant. And from carrying on solving all of the constraints on the previous side, we pull out that our alpha I is given by this expression here. So it's actually proportional to a time derivative. So under PT, specifically the time reversal, it does acquire a minus sign. And so our Hamiltonian, so the Swanson model, is PT symmetric. So we don't have any worries there now. The sigma function, which was present in all of those equations, satisfies this auxiliary equation here, which can look kind of messy, but it does reduce to nice solvable equations for different choices of R, S, and alpha R. So for example, you could take it to be alpha I as being 0, and your alpha is then fully time independent with these choices, and you pull out a nonlinear Ermakov-Pinney equation. Or you could take your alpha to be completely complex and fully time dependent, and you also get another nonlinear Ermakov-Pinney equation. And there are also other choices here. And usually you pull out a nonlinear Ermakov-Pinney equation, but this has known solutions, so that's fine. Now that we've constructed the point transformation, we should move on to step 3 of the approach that we discussed. This is acting with the point transformation directly on the reference Hamiltonian, the time independent reference Hamiltonian. And in doing so, we pull out this invariant here, which is an invariant for the time-dependent Swanson model and is non-Hermitian, as can be seen from the eyes all over the place. The different reference Hamiltonians I discussed earlier, so the free particle and the linear term and so on, they obviously lead to slightly different point transformations, and they also lead to slightly different invariants, but they are all invariants for the time-dependent Swanson model. Moving on from here, then we now need to complete step 4. So that is determine the Dyson map for the time-dependent Swanson model. We noticed that all of the invariants for all of the different reference Hamiltonians we considered could all be written in this form, where AR, BR, CR, CI, and so on are just real time-dependent functions, and that all the invariants satisfied this property here. So there were ratios of the time-dependent functions, which were all equal to this. This made it very straightforward to identify a Dyson map as being an exponential of a time-dependent function multiplied by x squared. Given that it's real, it's nice and straightforward to now compute the metric from this. It's just that squared. And we can then substitute it into the time-dependent Dyson equation to pull out the Hermitian Hamiltonian. So here we have it that it's a time-dependent harmonic oscillator with a time-dependent anti-commutator XP term. And we have completed the 4-step approach. So we have gone from a stationary harmonic oscillator to finding the Hermitian Hamiltonian related to the time-dependent Swanson model. My conclusions. We have shown for the first time that you can use point transformations with non-Hermitian Hamiltonians. This had only been done in the Hermitian regime before. It has increased the number of steps to find the Dyson map, but it has bypassed the need for an ansatz for the invariant. And we've actually started looking a bit more at more complicated models where it would have been very difficult to find a correct ansatz for an invariant for those models. So this procedure really does help with that. Because we are using then the invariants to determine the Dyson maps, it actually makes it easier to determine these Dyson maps, and therefore it's also easier to determine multiple Dyson maps. We've recently been looking at some work that we've been doing on an infinite series of Dyson maps where we can use 2 starter Dyson maps to determine an infinite number of Dyson maps. So this approach very much helps with that as well. I didn't go over this here, but it is in the paper. The reference Hamiltonian, so we chose the harmonic oscillator, doesn't need to be exactly solvable for you to produce an invariant for your target Hamiltonian. And it also doesn't need to be Hermitian. So we also looked at the, for a target Hamiltonian being the time-dependent harmonic oscillator with complex linear turn. We just took that as our reference Hamiltonian, the time-independent version. now it would be very good to apply to more complicated systems, which we have started doing, and the approach still holds up well and is straightforward to carry out. But after all that, thank you for your attention, and I'd like to answer any questions.
Thank you, Becky. Very much, Becky. Philip has a question.
Yes, first of all, thank you. That was very, very interesting. I'm wondering the following. With the Swanson model, you have A squared and A dagger squared. You could make a Bogoliubov transform to a quasi-particle basis. Maybe you could not do that in the time-dependent case, in which case what you've done would be superior. That's the comment.
Oh, thank you. I'll have to have a look at that. Thank you.
I can maybe comment on this. In the time-independent case, I wrote a paper with Fabio where we just did that. We carried out the Bogoliubov transformation. But in the time-dependent case, the problem is this additional term, which looks like a gauge transformation term, but isn't, because the transformation is non-unitary. And I don't know if this came across to everybody. The four-step method consists of reducing this complicated equation with this additional term. Maybe you show this again, Becky. You can also summarize this again. Yeah. So that term makes it very hard to solve this equation. But when you go over the invariance, you reduce the problem to a similarity transformation. Becky told this all very nicely, but it's very technical and difficult to digest. So what she just marked there, that makes the problem extremely simple compared to the full equation. That's the key point. And now to find this invariant, yeah, that is all what these point transformations were about. Yeah. So this is, in a way, if you want to look at it in this way, it's an auxiliary problem.
Yes, that I appreciate.
Okay, I just wanted to repeat. So
no, that's very nice. But I'm wondering whether this thing that she's highlighted, that Becky's highlighted, could you now go back to the Bogoliubov problem and try to apply this technique?
Oh yes, because now it looks like a standard problem for Hamiltonians, and now you can do everything you could have done in the time-independent case. Because time now here is now just like a parameter. Oh, I see. You know, that one could do, of course.
Oh, very good.
For the Swanson model, but this is very general. So
yeah, for Swanson, yes.
Yeah. More comments, more questions?
I have a question. Well,
yes,
a couple of questions and a comment. The question previously commented about the invariant, the way of transforming the Hamiltonian. I didn't understand very well, but I think I agree with, because when you apply a point transformation, the Hamiltonian is not transformed correlated. What is transformed are the equations. Schrodinger equations goes to Schrodinger equation with the new. So you have to take into account also the partial derivative with respect to time that changes with the point transformation. So equations transform into equations, but Hamiltonian, I think they don't transform into Hamiltonian.
No, so the reference Hamiltonian here becomes the invariant of the other system, because it
yes, the invariant it becomes the invariant. Okay, yes.
It preserves conserved quantities, these point transformations. So in the time-independent system here, it's a constant of motion. So it should also be a constant of motion when we apply the point transformation to it. So it becomes the invariant.
Yeah, of course, because point transformation transforms invariant into invariant.
Yes, okay. I think I can just rephrase what Giulio asked a moment ago. The question is whether the new H is the generator of time translations, as opposed to simply being what the old H becomes. See, the old H was the generator of tau translations by construction, but is the new H automatically the generator of time translations for the new system? I mean, that's related to what I was asking earlier about whether or not you might mix in some momentum generators. I mean, I'm perfectly happy with what you've done. I mean, it's okay. I mean, and your H is an invariant, but I think it may not necessarily be the generator of time translations. That would be a concern, but not. Yeah.
No, it is. It is.
I
mean, because it is by definition, because there are two steps. So as Julio said, you're transforming differential equations, and you're transforming from one Schrödinger equation to another Schrödinger equation. But the invariant isn't here yet. That's the next step. Once you have the transformation, then you are acting, here it is, yeah. You are acting on the time independent one, but not on the entire equation. And that gives you the invariant.
Oh, okay.
So it's more like it's on the eigenvalue equation, not the time-dependent Schrödinger equation to pull out the invariant.
So the way to get the gamma is transforming one equation to another.
Oh, okay. Good.
I have another comment, not a question, but a comment. What about non-point transformations? Have you thought about them?
No.
Because point transformations are very nice because they preserve symmetries. They preserve all the geometric structure of the equation. So it's, but you can also have non-point transformations. They preserve other kind of symmetries, contact symmetries, which are more general than point symmetries. But you can still transform equations, differential equations into differential equations. And in fact, in a recent work, we have found some transformation that change one system into another system for the simplest case of the harmonic, the family of the harmonic oscillator into another time-dependent harmonic oscillator. Where because if you see the transformation of time, if you go forward to the simplest case where just the tau depends just on t, you see that tau is a differentiable in time, but it's non-trivial and has a particular form. Okay, it's fixed by the condition that the Schrödinger equation goes to the Schrödinger equation. But you can, if you impose, you look for a transformation that fix the time, so tau is equal to t. So this the time, the way of measuring time is the same in both systems. Then you see that you obtain that the transformation cannot be point, but it can be a non-point transformation. But in fact, it transforms any system of this same kind, any harmonic oscillator with time dependence, time independent frequency and mass into another of the same kind. So you can find this kind. And even though this kind of transformation do not preserve symmetries, but in this case, they preserve the differential equations and move.
But that's not enough. The key here is that they preserve the conserved quantities, because what we're after is the invariant.
Yeah, but in this case, they behave, if you choose, I mean, you can do the same, you can play the same game and it preserves everything. So I can give the reference to my paper.
Well, if they preserve the conserved quantities, then it's fine. Then there's another option. Yeah.
We have done just for the case of the free particle into another system, but you can also do it for the harmonic oscillator, time independent harmonic oscillator into a time dependent one.
Well, it needs to be non-trivial invariants. Yeah. Last question.
Just a question concerning Julio's comment. Is it possible to relate these contact transformations or to reinterpret them as a kind of Lie symmetry, generalized Lie symmetry, so that you have a kind of killing vector or something like this in your system? Is it possible to map this, or is it something very different?
Yes, I think they are least, but they are generalized Lie because normally one thinks of point transformation, Lie transformation are geometrical transformations, but you can generalize to transformation that that also change the momentum independently. So that they are non-canonical transformation which are not point transformation. So
yeah, so it's a kind of Lie derivative then on the phase space or something like this, a generalized phase space.
Yes, I think so. I think it's but the point, the problem is that there are an infinite number of contact transformations. So
Yeah,
one
sure,
can see.
sure. Yes, yes.
So it's more complicated.
Okay. Thank you.
Thank you, Becky. I think we have to move on. Thank you.
Thank you.